As you're viewing this video today, I hope that you have your notes printed or at least visible for section 7-3. We have three new ways of showing that triangles are similar. If you recall, the definition of similar polygons would say that we're able to find similarity between polygons if all of their corresponding angles are congruent and the ratio of all of their corresponding sides are in proportion. Now, the problem with that, just like remember the definition of congruent triangles, in a triangle there'd be 6 different things that we'd have to show. We'd have to show all of the angles congruent from one triangle to another, and all of the side lengths from one triangle to another are in proportion. So that becomes rather cumbersome. So in other words, to show that two triangles are similar, we really don't want to use the definition of similar polygons. That would be something that after we already know the two triangles are similar, we could use those qualities. Kind of like we did with definition of congruent triangles. Didn't use it to prove triangles congruent, but once we knew they were congruent, then we used that quality from the definition. So let's just review what we have now in section 7.3 as other ways or shortcuts for showing that two triangles are similar. We had, first of all, a postulate. And a postulate's one that if we were looking at it in terms of inductive versus deductive reasoning, it's really an inductive reasoning thing that we're just going to accept as a rule. So AA similarity, recall, means that if we know two angles in one triangle are congruent to two angles in a second triangle, the triangles are going to be similar. So then from the definition, we could show that the ratios of the corresponding sides are in proportion. A second way would be SSS similarity. And we want to be careful here, make sure that we show the similar symbol with the tilde, because we also had an SSS for congruence. So this one's a little bit different. This one's saying if we know the ratio of the corresponding side lengths are proportional, then the two triangles are going to be similar. Notice we don't have to know any angles then. But once we have this, then we could say, oh, by the definition then, all of the corresponding angles have to be congruent. Finally, we have SAS similarity. And kind of like congruence, two sides and their included angle. So here, those two side lengths from one triangle are proportional to the two side lengths that correspond in a second, and the included angles have to be congruent. So again, that's in your notes. I'm just reviewing here. Now we want to look at an example, and this type of a figure is one that kind of creates some difficulty, which is why I wanted to make special mention of it. We have what looks like a triangle and then a segment in it. But if we look closely, there are really two triangles in the picture. One is just nested inside of the other. So in order to help me find that value of x, I have to think, okay, could I first of all show these two triangles are similar to each other? If so, then I know that their corresponding side lengths are proportional. I can write a proportion to help me find that value of x. So in order to use SAS or AA or SSS, I need to think about the information that I already have. Now, as it's labeled, I only know a few things. I know that the length of the segment from here to here is 20 centimeters. I know each of these lengths, 15 centimeters and 18 centimeters respectively. And I know that these two segments are parallel to each other. Now, let's key on that. Because remember, if two lines are parallel and cut by a transversal, then we have some angle pairs that are congruent. So, for example, if I think of this segment as a transversal between those two parallel lines, I'd be able to say that those two angles are congruent by the corresponding angles theorem. Two lines cut by a transversal, then their corresponding angle pairs are congruent. I could use the same idea to show those two are congruent, or note that this angle is actually in both the smaller triangle and the larger triangle, so I could say that angle is congruent to itself. And the reason for that would be by the reflexive property. Let's go with that one, although I could have chosen those two. So I know the triangles are similar by AA similarity. Now, it's still kind of difficult to see what's going on there, so I'm going to pull those two triangles apart so I can look at what corresponding side lengths we'd have and so on. So if I look at the larger triangle, and I'm just going to produce a smaller version of that, I know that this distance is 18 centimeters. This entire distance would be the sum of these two lengths. So this would be x plus 20 centimeters. In the smaller triangle, again, I'm just sketching this, so it doesn't have to be perfect. This distance is 15 centimeters, and this distance is 20 centimeters. Now, I want to label my angles within this picture too, so I know that this angle and this angle are congruent. This angle and this angle are congruent. And in our original picture, those are the same angle. So now I can figure out my corresponding sides. Notice that the one I want to try to find here, the x, is a part of this length. So x plus 20 in the triangle on the left, notice it's between these two angles. That would correspond to the 20 centimeters for the triangle to the right. So notice my order. Numerator was the triangle on the left, denominator was triangle on the right. So I want to keep that same order. So triangle on the left, I also know that one's 18 centimeters. So corresponding to the triangle on the right would be 15 centimeters. Now, I can make this proportion a little bit easier to work with by reducing. In a proportion, remember that means two ratios equal, I can reduce vertically, just like we always do with fractions, but because I could switch things on the diagonals, I could also reduce horizontally. Remember, if this is multiplication, we can't do that horizontal reducing. And because this is a proportion not multiplying, I cannot do diagonal reducing. Diagonal reducing is only if that's times. That's why it's really, really important that you put an equal sign in a proportion. And you put a multiplication symbol, a dot, if it's multiplication, because the rules are a little bit different in those. So, here's what I'm thinking. I see that 3 is a factor of both 18 and 15. So if I divide both the numerator and denominator of this fraction by 3, I'd get that reduced fraction, 6/5. But I have another reduction horizontally. 5 is a factor of both 20 and 5. So if I divide this by 5, divide this by 5, now my proportion is a lot easier to work with. So when I do the cross products, and you don't have to put this in, but it's helpful sometimes to remember in an equals, for a proportion, if I multiply diagonally across that equal sign, the resulting products have to be equal. So x plus 20 times 1 would be x plus 20. 4 times 6 would be 24. So now when we subtract 20 from each side, x is equal to 4. If I just check that, if I put 4 in for x, I'd have 24 twentieths. Is 24 twentieths the same thing as 18 fifteenths? Yes, they both reduce to be 6 fifths. Now, just real quickly, I want to show, because you don't have to reduce, what would have happened if we would not have reduced our proportion to begin with. We would have had x plus 20 times 15 equaling to 20 times 18. Well, I know 2 times 18 is 36, so 20 times 18 is 360. If I distribute, subtract 300, divide both sides by 15, I'd still have come up with the same solution. And it kind of depends upon what your preference is. You know, if you like working with smaller numbers to multiply and divide, that's fine. But sometimes we forget about how to reduce in the proportion. It's completely up to you there. I wanted to show you this kind of an example where we had a triangle nested inside of another triangle, because that sometimes is difficult for students to see that. Thank you very much.